Juniors, it's Mr. Reynolds here. Looking forward to starting our astrophysics unit with you. This unit's pretty interesting. There's really two main topics to this unit. The first topic we're going to start with, we're going to spend 3 weeks on, is looking at stars. Looking at what happens inside stars, what are the different types of stars, how are they born, how do they die, what happens when they die. Really interesting things. A lot of the stuff we're going to talk about when it comes to stars is just absolutely mind-blowing. Some of the values and some of the numbers we'll deal with are just out of this world. Next, we're going to take a look at the universe as a whole. Look at how the universe was born, how the universe has grown, how it's changed, how it's going to potentially die, and how do we know these things? We call that cosmology, looking at the universe as a whole. But today we're going to start by just talking about stars in general. Now you'll notice in your assignment I have you look at several other things in the universe, and that's very important to look at. However, stars are going to be our focus. First of all, what is a star? Well, a star is basically a big ball of gas. Now, the reason stars are shaped like a sphere and not necessarily like a terrible star shape that I draw, is that gas is all pulled together by gravity. All the gas is being pulled together by gravity, and it turns out when all the gas is pulling on itself, it's going to try to take the smallest volume it can, try to squeeze everything as tight as possible, and that kind of shape is actually a sphere. Now, of course, in the real world, yes, stars do rotate, so it could be a little bit non-spherical, but for the most part, we're just going to consider these stars a sphere. Now, as I said before, a star is just a big ball of hydrogen. Now, we have tanks of hydrogen, so you may ask, well, why does it glow? Why does it have all that energy? Well, a star has all this mass. It's a huge, huge, huge amount of mass, and it's enough mass where all of this gravity, this immense amount of gravitational force, all pushing in. When you get to the center of that star, we call it the core. When you get to the core of the star, the gravitational pressure is so great that the gas inside that star, that gas almost always is hydrogen, unless the star is starting to die and it could be bigger stuff. But for the most part, it's going to be hydrogen. Those hydrogens start getting squeezed together into heliums. So the physical identity of the atoms are actually changing. We call this nuclear fusion. This nuclear fusion, this process, gives out some energy. And so that process of the hydrogen squeezing together to be helium gives off a little bit of energy. That energy escapes. It takes a long path outside. Usually takes about 10,000 years, the energy to get to the surface of the star. And then that energy flies away at the speed of light, warming us up, giving us sunlight and all that kind of stuff. So this is in general what a star is. In this first lesson, what I want to do is I want to talk about two main ways we're going to classify these stars. And I want to make sure you know the difference between these two terms, because the difference is going to be very important for us. Some of the things we talk about here, you will actually see again next year when you study environmental physics. Because in environmental physics, you're actually going to take a look at the sun and see how hot the Earth is due to the sun, and you're basically going to use the same equations. So we're going to talk about two terms today about a star. If you, by the way, B.1 in the data book, it's on the last page, stellar quantity. There are three equations. We're going to save the first equation for the second video, but the second two equations are the two variables I want to discuss. The first variable is luminosity, and then we have brightness. Luminosity and brightness. These are two terms that sort of seem like they might be very similar, but they're actually quite different. And so let me ask you this. I'll ask you this first question. We use this example. If you look in the sky and you see a star that is medium brightness, it's not the brightest star, it's not the dimmest star, it's average, it's right there in the middle. Does that mean that the star has an average amount of energy being given off? Well, maybe. It could be a very small star very close. It could be a medium star, a medium distance away, or it could be an incredibly intense star very far away. And therein lies the difference between luminosity and brightness. Luminosity, the definition for luminosity is the energy given off per unit time by the star. Now, you may be thinking, Mr. Reynolds, you say energy given off per unit time. So basically, luminosity is energy over time. Mr. Reynolds, we've seen that before, but you didn't call it luminosity. You called it something different. What did we call energy over time before? We called it power. And that's exactly what luminosity is. Luminosity is a fancy word for power. It's the word that astrophysicists use for power. It's how much energy that star gives off every single second. Just like power, the unit for luminosity is going to be the watt. Now, if you want to take a wild guess, are the luminosity of stars going to be or small? Obviously, the luminosities are going to be absolutely immense. Stars give off an absolutely absurd amount of energy every single second. And so the numbers are going to be just mind-blowingly crazy. So typically what people might do is they might give you a luminosity in terms of solar luminosities. So they might say the luminosity of star A equals 10 times the luminosity of the sun. Often, and we're going to get into this a little bit more next week, and maybe even a little bit later in the next video. But oftentimes people will give you luminosities in terms of solar luminosities. So just watch out for that. And the equation for luminosity is given to you in D.1, and it says luminosity equals sigma, it's a lowercase sigma, A T to the fourth. Again, this L stands for luminosity, measured in watts. T stands for temperature. Now, temperature, whenever you have a temperature by itself, it can only have one unit, and that is Kelvin. Thankfully, in this chapter, all temperatures are going to be given in Kelvin. There's no need to ever do anything in Celsius with star stuff. A is the surface area of star. Now, the surface area of the star, we're going to say it's going to be a sphere, and so that's going to be a 4 pi r squared. It'll be the surface area of the star. Sigma is a value called Stefan Boltzmann's, forgive my spelling, constant. This is a constant value. It is given, it's done by somebody Stefan and somebody Boltzmann. There's probably two people there. And the value for this is 5.67 times 10 to the negative 8th. Of course, you can find this in your constants page. And the unit for Stefan Boltzmann's constant is watts per meter squared Kelvin to the fourth. Sort of weird unit, but if you'll sort of look at how the equation works, it'll basically cancel out all the units properly. The easy way to remember this is it's 5.67 times 10 to the negative 8. 5678. That's how I remember that value. So this equation will help you find the luminosity of the sun. And if you plug in the values for the sun or star or anything really, you're going to get absolutely immense values from this. Luminosity is completely independent of where a star is. If a star has a large luminosity, it is very luminous, whether it's right next to me or very, very far away. Now, brightness is a little bit different. Brightness is not a property of a star. Brightness is the intensity of a star at an observer's position. Just like luminosity matched with power, brightness is intensity. So if I see a very bright star very far away, it's going to have a low brightness, even though it has a very high luminosity. Likewise, a low luminosity star very close will have a high brightness because it's very close to us. The sun is a medium luminosity star. It's pretty normal, pretty average star. But for us, it has a huge brightness. Brightness of the sun is incredibly high because the sun is, well, right next to us. The distance is very small. Now, like I said before, brightness is power. Light. That light from that star spreads out in all directions. It spreads out in a spherical shape. So by the time that energy has gotten to us, that sphere is expanded, spreading out that energy, making the intensity less and less. We're going to use watts for that. A stands for area, meters squared. But of course, you remember what is power really in this chapter. Power matches with luminosity. So we'll say intensity equals luminosity, which is just power, over 4 pi d squared, where d is the distance to star measured in meters. You'll notice 4 pi d squared, that's basically the surface area of a sphere, because that is the shape upon which the energy has been spread out. So we have two equations, and by the way, this is not intensity, this is called brightness. So, luminosity and brightness. Which of these two values do you think we could easily measure here on Earth? Well, the brightness is very easy to measure on Earth. That's what a camera does. You point a camera in the sky, take a picture, it measures the brightness that you're looking at. Luminosity is a little tougher. Luminosity requires a few techniques we'll talk about in the next video. Let me give you one example of how this equation could, or how this problem could be done. Let's say you have two stars. So let's say the temperature of star A. What is luminosity? Luminosity of star A in terms of luminosity of B. You're going to see a lot of problems in this chapter talking about in terms of. So let me give you an example of how you solve this. We solve this with a ratio. So the question is asking, what is the luminosity of star A? So I'm going to say, okay, LA over in terms of luminosity of B. So I'm going to solve for this ratio, luminosity of A over luminosity of B. Now, what I'm going to first do is I'm going to write down the equation for luminosity. Now, if you remember above, the equation, luminosity, this equation right here, is Stefan Boltzmann's AT to the fourth. So let's write that out. Stefan Boltzmann's AT to the fourth, and of course this is A, so I'll put object A, Stefan Boltzmann's AB, TB to the fourth. All right, that looks good to me. Now we're going to expand that out because we do know the area of a star is 4 pi r squared. So Stefan Boltzmann's 4 pi r a squared t to the fourth over Stefan Boltzmann's 4 pi rb squared t to the fourth. And then we can go about canceling. because I don't know what the temperature of the star is, but I know the temperatures are the same. And so I can cancel out the temperatures because those are the same things. Anything else I can cancel out? Well, I can cancel out Stefan Boltzmann's constant. I can cancel out the 4. I can cancel out the pi. And it turns out that this equation is going to simplify to RA squared over RB squared. Now, I don't know the radius of either star A or star B, but I do know that star A has twice of star B. So the radius of A equals 2 times the radius of B. I can go ahead and plug that in. So 2 times radius of B squared over radius of B squared. If I square that, I get 4 RB squared over RB squared. Of course, the RB squareds cancel out, and I'm left with LA over LB equals 4. Now, the question was, what is the luminosity of star A in terms of star B? So I can rearrange this equation and say the luminosity of A is 4 times the luminosity of B. That's how I would answer that question. I don't know the luminosity of A or B. Don't know them at all. But I do know that the luminosity of A is 4 times higher than the luminosity of B. This is a common type of problem you'll see. Using this ratio setup is very common in this chapter. We'll be doing it quite a bit, including some you'll probably see next video. See you then. Hopefully this makes sense. Hope you have a good day. Thank you.